So the plan is, go ahead and leave it open. Plan is I'm going to talk about tins. We're going to talk about tins, and then we're going to talk about. Yeah, it is. Talk about tins, then we're going to talk about floodplain delineation. And so those two topics, and then we'll have some time, I think, after that for you to work on your own, and you'll be able to go through the HEC-RAS tutorial and use HEC-RAS, learn how to use HEC-RAS, okay? So let's first talk about tins. Tins are, we've talked a lot about DEMs. We've talked a little bit about tins. If you remember, TIN stands for Triangulated Irregular Network. And all it is just a bunch of XYZ points connected by triangles. And we're going to learn about some of the WMS tools for creating tins, editing tins, and okay. Now let's leave the door open. Let's leave the door open because it keeps it cool in here. So, there are different ways of getting tins into WMS. We're going to talk about some of those. And you can always convert between, if you have a DEM, you can create a tin. If you have a tin, you can create a DEM from that. This is a tin, and a tin is just scattered XYZ points that are connected by triangles. And there are several ways to get tins into WMS. One way is if I have just XYZ points, I can read those XYZ points into WMS and triangulate them. Also, if I have a contour map, I can point and click along the contours and create those contour elevations as vertices on your tin and then triangulate. I can convert a DEM to a tin. If I have CAD data, sometimes you have CAD data that's contour data, and you can convert that to a tin. And also there's LiDAR data. Do you know about LiDAR data? Familiar with that? Yeah, you fly, it's where you have a plane that flies over an area.
It costs too much.
It probably does.
In Africa, it was 1 million euros. 1 million euros for area, for the floodplain area only.
Is there any virtual LiDAR data available online?
Any LiDAR data available online?
Even all the missions?
Yeah, so there is LiDAR data available online, but probably not for Africa. It's probably for the United States, Europe, Canada, those countries. Maybe some parts of Asia, but probably not Africa. It requires you to fly a plane over an area and you run a laser down to the ground and get the feedback from the laser, and it just is it's probably, like you say, it's too expensive. €1 million.
But the only for irrigation there also, because once the polluter is very
I think this LiDAR data is just very detailed, dim, right?
Yeah. It's a DEM. It could also be a tin. So it's actually scattered XYZ points, but there are ways of converting between that, from that to a DEM, to gridded elevation data, and converting back and forth. So
can we improve the DEM by surveying? Like, for example, we have a watershed usually, and normally our surveying team focus on one specific area or some areas, and then we have more points in detail.
yeah,
Then we merge both of them, use one DEM like that.
yeah, yeah, you can.
We can do it.
As long as everything's, as long as you can get everything in the same coordinate system, then you can do that. So you can import XYZ file into WMS, and WMS has this thing called the File Import Wizard, where you can read in XYZ data, and you read them in as 10 vertices, and then after you read them in, you can triangulate your 10 and get your contours. Another thing you can do is there's a digitized tool in WMS that allows you to point and click. If you have a contour map, you can point and click and create vertices on a 10. And if I have a DEM, like I mentioned, you can convert a DEM to a 10. There are two options. You can just convert all the points to a 10, and you can also convert selected points to a 10. So if I do all the points, you just have a whole bunch of triangles that are in the rectangular format. If I do selected points, then WMS will only convert the most important points to a 10. You can also do, I'm not going to talk much about this, but you can, if I have a watershed, I can define a watershed boundary or whatever, define my streams, and then WMS will create a 10 from that watershed. But if I have CAD data, so this is a CAD file that I have in WMS, I can go to that CAD data and convert that CAD data to a 10 using this CAD menu up here, CAD to 10. When I do that, WMS will create a 10 from the CAD data, and the contours are connected by triangles. Sometimes I might have triangles that look like this, so the data may not be very good in these areas because they're connected using, these are the same contour values in this area here. So you can also, if I have a shape file with contour data, I can read in a shape file, so GIS data, and each contour has, let's say each contour has an elevation value. I can create feature objects out of that and then convert the feature objects to a 10. If you do have LiDAR data, you end up with a bunch of points, and it's a good idea to thin out those points. And WMS has some tools for filtering out points, and the tool that you use in WMS, you define an angle, and the angle is the angle between these normals on the adjacent triangles, and if those normals are less than a certain angle, then WMS will delete the vertex between those the normals. And so originally if I read in some LiDAR data, it might look something like this, but then as I filter it to different angles, you can see the number of vertices are decreased. And so this is if you have LiDAR data. If you have too much data, which probably isn't a problem here. Here you have too little data. But if you have too much data, then you'll need to thin out your data. And somebody did a study with different angles of filtering, and they discovered that if you filter to 8 degrees, then you'll end up with 16% fewer points, but you will still get an accurate hydraulic model. So you'd use the 8-degree filtering. But for here, that's not something you'd use unless you have LiDAR data. So there are different display options for tins. You can contour them, and just like DEMs, you can contour. You can do color-filled contour, contours, and they're just different display options for tins. You can also convert a tin to a DEM. So here's a tin. I can convert that to a DEM. Also, if I have two tin data sets, so maybe I have a tin that I created from a DEM, and then I have another tin from survey data, like you were asking, I can merge these two tin data sets together. So here I have a tin, and I convert my DEM to a tin. I can merge these tins together, and then the data is merged. So you have something like this. So DEMs are widely available online, but tins are used for survey data, so they're a little bit more intelligent, you might say. They're just kind of the most important. They could be the most important points in your areas. Instead of having gridded elevation, it's just XYZ points. And WMS provides a lot of tools for working with tins. We'll go through some of those tools. Before I show you a demonstration, I wanted to talk about floodplain delineation a little bit. In floodplain delineation, the only way to delineate a floodplain in WMS is if you have a tin. And so if you have a DEM, you can convert that to a tin and use the DEM-based tin to do your floodplain delineation. But you have to have a tin to do a floodplain delineation. And I want to talk a little bit about floodplain delineation. So before GIS, people delineated a floodplain from a contour map. So they take a contour map like this, you take your river stages and extend your river stages over to your contour values, and you would hand delineate a floodplain. So this is how you delineate a floodplain before GIS data were available. And it was lots of hard work to delineate a floodplain. In WMS and in other tools that are used to delineate floodplains, you read in your river stages or your water surface elevations into the program, and you can interpolate water surface elevation so you have additional solution points. So you interpolate water surface elevations along your streams and along your cross sections. The idea is that you have to get as many water surface elevation points as you can get, and then you look at each point on your DTM, your tin. DTM stands for Digital Terrain Model. When I refer to DTM in WMS, that could either be a DEM or a tin. So DTM could either be a DEM or a tin. In WMS, though, you can only delineate a DEM from a tin. So if we look at a point on our tin, WMS looks for surrounding water surface elevations, and if those surrounding water surface elevations are higher than the point I'm looking at, so this point right here, then WMS sets that as a point that's flooded, and there's a water surface elevation that's associated with that point. So WMS is able to compute a floodplain boundary. This is the way to do your floodplain boundaries in WMS. You can get your water surface elevations so in WMS, to do a floodplain delineation, you have to have your elevations, you have to have your water surface elevations, and those could be computed using HEC-RAS, or maybe you know what the water surface elevation is, or maybe you just run the Manning's equation, and you can enter a water surface elevation from Manning's equation at different points on your river. And so somehow you have to get your water surface elevations. Then WMS will compute a flood depth data set, and you can create different kinds of maps in WMS. So To do floodplain modeling now, you get your DEM, your tin, you get your water surface elevations, create a level water surface, so that's your 2D scattered data set. You take your water surface elevation data set minus your tin elevations, and then that's your flood depth, and you can create your water surface elevation data set. So there are several ways of getting your water surface elevations that are available in WMS. You can manually create them, just point and click and create them in the 2D scattered data set. You can use the channel calculator. There's a channel calculator in WMS that allows you to do that. You can run HEC-RAS, read that in, or if you have some X, Y, and water surface elevation points, you can import that file and read in those points. So you can manually create the points, use a channel calculator, and this is the channel calculator in WMS. You can define a cross section, and this just uses Manning's equation for a channel. You can import your water surface elevation points from a text file, and you can run HEC-RAS like we've seen. So to create a good water surface, you need to interpolate your water surface elevations. You need to get as many water surface elevations as you can. And so this is a HEC-RAS model that I ran. These green dots are my water surface elevations. I can get additional water surface elevations by using this interpolate command in the 1D centerline coverage. Then I have these additional points. And if I use the interpolate command in the 1D cross-section coverage, I'll have additional points along each of my cross-sections. Then I can interpolate those water surface elevations to my tin, and this floodplain delineation dialog is where you do that. Just run your floodplain delineation, and then you end up with a floodplain that has your flood depths and your water surface elevations in my floodplain. One of the important parameters, so if I go back to this floodplain delineation dialog, one of the important parameters is this maximum search radius. Another important parameter is the number of stages in a quadrant. And let's talk about what those mean. So the max search radius, when I delineate a floodplain, WMS looks at each point. This is my tin here. It looks at each point on my tin, on my elevation data, and tries to find water surface elevation points. These blue points are my water surface elevation points. Those are my water levels. And WMS tries to find water surface elevation points within a radius of each point on my tin. And so the radius you define is the radius that WMS is going to use to search. So here in this window here, I've entered a radius of 100. That means WMS is going to search for each point on my tin, on my elevation data set. WMS searches 100 meters, uses a 100 meter radius search area to find water surface elevation within that 100 meters. If it can't find any water surface elevations, there's no flooding at that location. If it can find water surface elevation, it finds however many it can and uses an interpolation method, inverse distance weighting, to determine the water surface elevation at this point from these surrounding points. Okay, so that's how WMS delineates the floodplain. Another parameter is the maximum number of points, so number of total stages that WMS searches for. And right here in this window, I don't have that option turned on, but it's set to 12. But it could be set to any number. So in this case, I'm only searching for the closest 8 points. And so any dark blue point on this image, WMS will use for interpolation. Any lighter blue point like these points that's not close enough, not as close to this interpolation point, WMS does not use. So it only uses the 8 closest points. And you can change that number if you want. What's that?
The number 3 again, because I missed it.
Yeah, so the number 3, I'll talk about that in just a second. But if I change the search radius, it has an effect on your floodplain delineation. So if with a 2,000 foot search radius, this is my floodplain delineation. And with a 3,000 foot search radius, it could change it. So I think I have some slides here that explain. Okay, so there is another number. This number right here, the number of stages in a quadrant. Let's talk about what that means. So if you have the option, let's go back to this window. There's an option in this window to use quadrants, and that's the default option. So with that option on, WMS looks at each point on my tin and divides it up into 4 quadrants. So these are my 4 quadrants, 1, 2, 3, and 4. And then for each quadrant, WMS tries to find points that are within the search radius for each of those quadrants.
Why you are trying to find water depths over each loop? I think after modeling completing the algebraic modeling, you know the water depths should be similar. I mean, you know the water level, and every node you have to subtract the ground level from the water surface to know the water depth. That's it.
Yeah, that's not exactly what we're doing here, though.
So why you are searching around the
The problem is if we just create a tin from our, let's say we have a tin from our water surface elevations, then we have a tin from our ground elevations. If we subtract one from the other, then we end up with points that are flooded that aren't, where there's no connection to the river, to the flood. So they may be flooded, but there's actually no flooding at those locations. So this is trying to, all these parameters, we're trying to make it so the flooding only happens where there actually is flooding. And so we can't just subtract one surface from the other. We have to have different parameters like the search radius and the quadrants to make sure that we get the most relevant water surface elevation points for each point on your elevation data. We need to find the most relevant water surface elevation points for each point on our elevation data. And the only way to do that, we have different methods of doing that. One way is a search radius and just use the closest points. Another way is these quadrants, and you get the closest points in each of these quadrants. So there are just different ways that we use to get a good water floodplain delineation. Yeah.
In this situation, the first situation, the only closest one, you will take this values or a ratio of these values.
And the one that I'm showing here,
Yeah, in the first one.
so this
In
one.
this situation, it has only 1 point.
So you could just use all the values within this search radius. And to do that, you'd have to turn this quadrants option off and set the number of total stages high to a high enough value where it gets all of those. Maybe I'm confusing people, but there are just different options. So the quadrants option, it divides for each point on my elevation data set, it divides it into 4 quadrants. And then the number that I enter is the maximum number of points WMS gets for each of those quadrants. So if I enter 3, then the maximum number of points that WMS is going to use for each quadrant is 3 points. So actually in this case I've entered 2 and it just uses 2 points for each of the quadrants. Any other point that's farther away is left out.
We have to use these two options, only one of them. When we use this one,
You have to use either one or the other. If you have the quadrants option turned on, then it's going to use this option. If you have it turned off, it's going to use the other option. This option right here, where it's going to use the closest, however many points you specify. So you have to use one or the other, but we found the quadrants option gives you the best result. So use the quadrants.
put the number 3 or 2.
3 is good. Just use the defaults. The only default you might want to change is the search radius. So you'll need to change the search radius. But the quadrants, you probably just don't change. Okay.
If we looking forward to determine our floodplain, so as far as I understood, we have to have a hydrograph entering this river, and then like water level in the downstream. So what only matter, what I think only matter is the amount of the water that enters the river. So if you have this hydrograph, like a huge amount of water, so the floodplain or the water will be flowing in the river and flooding these floodplains until the water is being finished. Yeah. So I don't understand why you are looking only for a certain circle. However, it should be calculated by hydrodynamics model to determine when the water will flood this area or not.
Yeah, so you could use a 2D hydraulic model and get the floodplain boundary. This is just.
I mean, if you haven't entered the water changing in time, so the water could so you have like this is the river and the water goes by this area, and then you have some amount of water will be stored in this rose tank.
Yeah.
And then after the water peak is passing by, this water will be reset and this water will remain in this place.
Okay.
So at the time you only look for this area.
Well, we're not considering time at all in floodplain delineation. We're just assuming that this is the maximum flood depth for anywhere in my floodplain. Okay.
So again, you mentioned water entering this river, because if you have like 100 years flood, so the water will be flooding a huge area, large area,
Now that's what we're doing is the 100-year flood. I'm not sure what you're asking.
So my question is, you are only looking for the point that near to the source of the water.
Yeah.
That with maximum elevation.
Yeah.
That should the water shouldn't overtop this point. Is it correct?
Well, I don't know. I'm not sure. I'm not sure what you're asking. So you're saying we're looking for the maximum. We're just trying to get a floodplain. Okay, that's all we're doing.
Okay.
And so we find the closest. This is how we do
My
it.
question is, you are not taking into account
Okay.
the changing in the water entering the river.
Okay.
The hydrograph entering the river.
Okay, we are. So you're running the peak flow rate. You're running the peak flow rate in HECRAS, right, or whatever model, and you're not doing it. It's just a steady state simulation. There's no change here. So you're assuming that the whole floodplain happens, the whole flood happens at once. You're just determining the maximum water level.
During the flood, it's not steady state. Unsteady state.
Okay.
So probably after defining this boundary floodplain, during the flood, another areas will be flooded.
Yeah, maybe. But this is steady. You're doing a steady state model. That means just do the maximum flow anywhere in your floodplain. That's all we're doing. We're not, and it's assuming the time could be anything. We're just figuring out what the maximum water depth is going to be for the flood, and it could happen at any time. I don't know. So, anyway, there are different options. I'm not going to talk about all these other options, but I guess I've shown you how to delineate a floodplain already. So what I'm going to show you now, though, is how to use TIN data. So there are a couple of ways of getting TIN data into WMS. One way is if I have an AutoCAD file, like some CAD contours, I can read these contours into WMS. And so here are some contours. Then I can go to the map module, and there's this CAD menu in the map module, and I can just convert this CAD data to a TIN. And when I do that, WMS creates this TIN, and these are the contours on the TIN. So that's one way to get a TIN. And if we look at the vertices, we can turn on the display of the vertices, maybe the triangles. So here's my TIN. These are the triangles on that TIN. And just got that from the contour CAD data. Another way I can get data into WMS is if I have a image. So I have an image like this. You can use something called the digitize toolbar, and so this down here, this window down here, I can get that by right clicking and selecting digitize, and turning on digitize mode. And so this map has a bunch of contours, and I can go in and create vertices using these contours. So this contour, I'll just enter the elevation for this contour, 7,400. That's in feet. And we'll select this create vertex tool and just go in and create vertices along those that elevation value. Okay, so you can do that. Then you can, maybe the next contour is 7440. Change the value and then go in and enter the values for that enter point and click and create points along that contour. So this is if you need to manually, if you have a contour map like this and you need to digitize the elevation. So that might be useful around here. And then maybe 7480 is the next one. I'll click and create that contour. I'm not going to do this whole map. This is a big map, but when you're done with this, you need to triangulate your tin. So to triangulate your tin, you right click on it, select triangles, select triangulate, and then WMS will triangulate your tin. And a lot of times when you have these contours, if you don't have data filled in here, you'll end up with these flat triangles. You can delete these triangles if you just select the select triangle tool and hold down the control key, drag a box or drag a line across here, select those triangles, and then delete the triangles. Hit the delete button, it'll delete those triangles. Okay, so those are some different ways of getting a tin. Another thing you could do is if I have a file like this text file with X, Y, and Z values, I can read in these X, Y, Z files as tin vertices. So I go open and then read this text file, and you can define different delimiters, how this file is delimited. That means whether I have tabs or spaces or commas, if it's comma delimited. And then I define this as tin vertices, and then this is my X, this is my Y, this is my Z value, and then hit finish. WMS will read those points in as a tin, and then you have to triangulate. So triangles, triangulate, and so here's my tin using that XYZ file. Okay, so those are just some different ways of getting tins into WMS. Another thing I wanted to show you is if I have, let's bring in some files that we have from the Nile River area, Cairo. So here I have some an elevation data set. This is just a DEM. Let's read in another elevation data set that I have, this Aster data set. Okay, so I have these two elevation data sets. Let's say I wanted to merge these elevation data sets together for some reason, or merge different parts of these elevation data sets together. Maybe one is more accurate than the other in a certain location. I can convert these to DEMs first. So let's convert this one to a DEM. Then we'll convert this other one to a DEM. So WMS is just converting this. This is a large elevation data set, so it's converting that elevation data set to a DEM. Takes some time. Okay, so I have two DEMs here. One of these DEMs I got from one source, another DEM I got from another source. Let's say I want to merge these DEMs together. Maybe I want to merge some part of these DEMs together instead of the whole thing. That would take a long time. So let's first I'm going to trim these DEMs so they're more manageable. Let's trim this DEM. Maybe to, let's define the area that we're going to trim. Trim it using a polygon. And we'll trim it to this area, let's say. So there's one DEM that I trimmed. Then I'll go to this this other DEM. Let's trim this DEM so it's a little bit smaller. Okay, so here's one of my DEMs, here's the other one. And let's say I wanted to merge these DEMs. One way you could do that is you could select both DEMs, right click and merge the DEMs. What this will do is it will use the DEM with the smallest cell size, and that will be the DEM information that's used wherever the two DEMs are, where they intersect. So my combined DEM, you can see the elevations in this area, the elevation contours are a little bit different where this other DEM was. Another thing I could do, if I convert this DEM to a 10, I can.
For merging two DEMs, it means that both of them have to be the same resolution.
They can be different resolutions, and WMS will just resample the DEM with the lower resolution, so it's the higher resolution. To merge DEMs, yeah. So first you bring in the DEMs. So you can bring in the DEMs by, there are different ways of bringing in DEMs. You can read them into the GIS, then convert them to a DEM, like I did. Or you can just right click on terrain data, select open digital elevation file, and that will read them in. Or you can go file open, and that will read them in somewhere. You just make sure there are DEMs under terrain data. Then to merge DEMs, you just right click, select two or more DEMs, right click, select merge DEMs. And then this window comes up. You'll define the cell size for the merged DEMs, and you usually want that to be the lower of the two cell sizes. And so that's what this number is that's displayed. Then you hit OK, and then it creates the merged DEM. So the steps are read the DEMs, select the DEMs, merge them, and then define you could change that number.
So you can have a smaller resolution.
If you wanted to do, but there wouldn't be any purpose in doing that because this is the smallest resolution of the two DEMs.
This is the quality.
Yeah, so that's as good as you're going to get. If you go smaller, it's just going to resample, and you'll end up with additional elevation points, interpolated elevation points.
Go for the same size as the DEM to merge the same size.
The same size.
As the image actual DEM, not the pixel in the resolution, but you mean the image size. You want to put
The default value for this resolution, so when I merge DEMs, the default value here is the smaller of all the DEMs that are, the smallest of all the DEMs that are selected. Smallest resolution. What's that? Yeah, just use the default. That's what you would normally want. But you could change it if you wanted. So this is the merged DEM. And I can, you know, so I have a lot of points in here. You can select these DEM points. It's going to be a lot of points. Those are the points on the DEM. Another thing you could do is, if I have two 10s, you can merge the 10s. So let's, I'm going to convert this DEM to a 10. I'm going to filter it. So we'll create a 10 here. So there's one of my 10s. And then I'll go to this other DEM. Let me actually delete some of these other DEMs. I think they're kind of bogging down my computer. So I'll go to this DEM. Right click and I'm going to delete that. That's my big one. And I'll also delete this other DEM. So let's convert this other DEM to a 10. We'll filter that one also. And so this is the other 10. I have two 10s here. This 10 I just created, yeah, things are kind of slowing down on my computer. I think I'm going to turn triangles and vertices off. So this 10 I just created was the lower resolution, so I'm just going to rename this to the lower resolution. And this first 10 is the higher resolution, so I'm going to rename that to higher. So that means the points are closer together. Then I can select to merge 10s. I can right click on one of them and select merge, and I can merge both of these 10s together. So I'll transfer them over here. So these are the 10s to merge. I'm going to merge all my 10s. Usually what I want to do is one area, if inside of one of my 10s I want to delete overlapping regions. And so for one of my 10s, it has elevation points inside of the other 10, but the other 10 has a more accurate data, so I would want to delete the elevation points from the lower resolution data set and That's what this option does. It deletes elevation points from the lower elevation data set, and then it retriangulates all the points in that data set. It's recommended to use that option. If you just merge all of the points on the tins together, then WMS is going to take all the points from both tins, even the overlapping areas, and it will just combine them into one single tin. And so your elevations might be mismatched in some areas.
If point has the same elevation. Sorry, if one point has different elevation in the two cases. One point has two different elevations.
Yeah, you could end up with the same point with two different elevations.
Error or pick one of them.
Usually the points won't be at the exact same location, and so it's going to use both of the points. And so you'd usually want to delete the overlapping points. And this window here tells you which tin has the highest priority. So this is, if you look at the help down here at the bottom of the screen, so down here at the bottom, I'm not sure how to point it out, but at the very bottom of the WMS screen it says list of tins to be merged. The tin at the bottom of the list has the highest priority, so you put the least accurate tin at the top, the most accurate tin at bottom when deleting overlapping regions. So we're going to put the tin at the bottom as the higher priority. So that's the higher resolution data. So the least accurate tin, that's the lower resolution, is going to go at the top. The most accurate tin at the bottom. So I just have to, and if it's just the opposite, I can move this up, move that down. When I hit OK here, WMS is going to merge those two tins together, and it'll delete any points inside one of the tins that is inside the lower resolution tin that's overlapping. So here's the merged tin. Let's turn off these other tins. Here's the merged tin, and that's what it looks. That's what the contours look like. Okay. So that's how you merge two tins together. It's how you merge DEMs together, stuff like that. So basically you can, if you have survey data, maybe you have somebody that goes out and gets some XYZ points. If you're trying to do a floodplain delineation, you can take your DEM to get the large part of the flood, to get most of the floodplain, and then maybe somebody goes in and does a survey of a stream or something. You can use that survey data to get more accurate data in the floodplain area near the stream. Okay. Any questions about this? Do you understand why I did this, or what I was doing, or have I confused everybody? Okay, you understand what I did. All right. Well, if there's no questions, what we're going to do is, we have an hour now, so 4 to 5. We've talked about floodplain delineation, HEC-RAS modeling. We've talked about SWIM, and we've talked about TINs. And there are several workshops, so if we go to the PDF files, the workshops that you can work on in the next hour, and you can kind of pick what you want to work on. But I guess if you're interested in HEC-RAS, probably the best one to do would be the HEC-RAS analysis workshop. So this one right here. But it depends on what you're interested in. If you're interested in SWIM modeling, you could do the SWIM workshop, which is this workshop 11A. 11B is the rational method. It shows you how to run the rational method. 13, workshop 13, shows you how to work with tins. It kind of shows you what I just showed you, so you might not need to do that one. Workshop 14 shows you how to do HEC-RAS modeling, and it would be probably a useful workshop. And workshop 15 shows you how to do floodplain delineation, and that one would also be kind of useful. So I guess the workshops I would recommend if you're interested in floodplain delineation are the HEC-RAS and the floodplain delineation, and then you could do some of these other ones some other time. So let's spend the next hour. We're going to go and do either the HEC-RAS or floodplain delineation or both workshops, and we'll do that. So we have till 5 o'clock. Another option you could do if you feel pretty confident, I guess. Maybe you have your own data. Maybe you have want to model your own area. You're welcome to create a model for your own area and just ask me for help, and I can come around and help people with their models. So either one.